I'd like to talk to you today about a very exciting time in my life when I was involved in the first clinical trials of reference point indentation. I was actually the first patient tested with it, but second was Davis Breimer, who's the CEO of Active Life Scientific. And the third was Alex Proctor, who's shown there in the background looking a little apprehensive because he knows he's going to be tested next. He's the Chief Technology Officer of Active Life Scientific. And the reason we consented to being tested by Dr. Adolfo Diaz-Perez there in Barcelona was that he was preparing to see if he could distinguish between the bone of patients who had had hip fractures from the bone of patients who had not had hip fractures. You see the weak bone, this was actually bone of a patient who had had a hip fracture. And you can see that as the indentation cycles progress, the probe goes deeper and deeper into the bone and has a bigger indentation distance increase than in the strong bone. This was bone from a control patient who had not had a hip fracture. And so these curves distinguish the bone of patients with hip fracture from the bone of patients without hip fracture. These results were published in the leading bone journal, the Journal of Bone and Mineral Research, JBMR, and we even got the cover. There you can see the reference point indentation apparatus that goes down. The yellow reference probe rests on the surface of the bone, and the blue reference point indents the bone. Down below you see a colorized view of an indentation made into bone with this instrument. This instrument actually creates microscopic fractures in the bone, but these microscopic fractures are so small that on the left there, compared to a dime, you really can't hardly even see them. So it fractures the bone, but in a microscopic way. Bone actually just contains all sorts of fractures and voids and blood vessels and so on already. So these extra little fractures are inconsequential for the strength of the bone, but they're enough to give a measurement of the bone's resistance to fracture. Each one of those dots represents an elderly woman who's in a hospital bed, either from a hip fracture, as shown in black dots, or from some other cause, as shown in red dots. What you see is that the indentation distance, which is how high the points are, is greater for the black dots on average than for the red dots. In particular, over 40 is all black dots, below 30 is all red dots, and in between there's some overlap. So the instrument distinguished between the bone of the women whose bone had fractured and the bone of women whose bone had not fractured, not perfectly, but very well, and surprisingly well as far as scientists are concerned. This was the first demonstration that bone material properties are different in patients with and without bone fracture. I mean, it's been known for a long time that how much bone you have, how much bone loss you've had as measured by DMD and T-score was relevant to fracture risk. But this is the first time that it's been demonstrated that beyond that, the material properties of the bone are relevant to fracture. And now that we know this, there's a chance to improve material properties. Once you can measure something, then you can work to improve it. And my hope is that work to improve the material properties of bone will result in a significant decrease in bone fractures as experienced by elderly people and even young people. Once we can learn how to improve bone material properties, we can move forward. The instrument measures other parameters. We can measure various parameters, and by combining many parameters get an even better picture than just the one that I showed you on the first slide. This is an interesting thing because it compares the reference point indentation values vertically with the bone mineral density horizontal axis. Notice that at about 0.55 bone mineral density, there are two patients. One patient has a broken hip, as represented by the black dot. The other patient did not break the hip, as represented by the red dot. Now the point is, if you only had a bone mineral density measurement, you would not distinguish those two patients. There would be no way of telling which patient was more likely to get the hip fracture. But with the addition of measuring bone material properties, correctly see which patient had the weaker bone and had the hip fracture. There's another similar situation up at about 0.75, where again, the red dot's lower than the black dot, showing that these two cases, which were indistinguishable by bone mineral density, could be distinguished by measuring bone material properties with reference point indentation. So we've shown that bone material properties are also a very important part of fracture risk. It's not just bone loss, it's also bone material properties. Bone material properties relevant to fracture risk can now be measured by the reference point indentation instrument. And now a new generation of therapies can be developed to improve bone material properties. Now, this study, like all studies, has limitations. It's a proof of concept study, validation of a novel technique. It was just one center, a limited number of individuals, restricted population, measured just one skeletal region, and so there's clearly need for further work. If you ever want to stump a scientist, what you ask him is, if he's talking as if, this has really been established now, okay, this is perfectly established. Ask them, well, do you think there's a need for further work? And this is just like asking someone who bakes pizzas, well, do you think enough pizzas have been baked? Or do you think there's a need for further baking of pizzas in the future? You know what they're going to say, and the scientist is going to say the same thing. There's always need for further work. And certainly in this area there's need for further work, but we're really happy with the beginning that's been made. Thank you.